Hello everyone, my name is Claire Babbitt, and for my final project, I decided to build a wearable running sensor. A bit of backstory is high-performance running watches give you biomechanical running data that you can use to help prevent injuries. The only downside is that these watches can range anywhere from $300 to up to $1,000. I sought out to design a custom biomechanical tracker from scratch using my Arduino and compare it to the results that my Garmin watch gives for the same runs. My device measures my cadence, ground contact time, and vertical oscillation, which are arguably the three most important pieces of data in running. A faster cadence means that less force is put on your legs at a time, and a faster ground contact time and lower vertical oscillation means you run more efficiently. I also then went and compared the accuracy of these results to my Garmin on different terrains, including sand, asphalt, turf, and grass. At the core of my device is a MPU9250 sensor, which is a 3-axis accelerometer, 3-axis gyroscope, and a compass all combined into one. It uses a 16-bit analog to digital converter, which allows for extremely precise results. To make this system fully standalone without connection to my computer needed, I wired a physical button to manually start and stop the tracking. The Arduino routes that data directly to the SD card module, creating a clean CSV file for me to analyze post-run. The entire device is driven by a 9-volt battery that I taped onto the back, making it completely on its own, just like a running watch. At first, I prototyped this on a standard breadboard that we were given, but I found that the violent physical impact of running caused the wires and sensors to come loose and sometimes fall out. So to ensure it could actually survive a run, I permanently soldered the entire architecture onto a PCB board and then applied electrical tape when I attached it to my shin. Now, let's take a look into the results. Obviously, we don't have time in 4 minutes to take deep dives on every single thing, but in summary, my sensor was fairly accurate. As you can see in the table, the hardware performed best on hard surfaces like the turf and asphalt, where the impact was sharp and distinct. It performed the worst on the sand and grass, where the surface was shifting and uneven. My biomechanics on the sand were also slightly altered because I was actively trying to keep sand out of the exposed circuit board in Arduino. To calculate my error percentages, I used my Garmin watch as the control value. I took the difference between the Arduino and the Garmin, and then I divided that by the Garmin's baseline. My cadence was calculated by tracking every time my right shin experienced a massive shockwave that shot past my impact threshold of 3.5 G. My sensor is measuring acceleration or the G-force directly on my rigid shin bone, so when my foot slams the pavement, a massive shockwave is created that runs up my tibial bone. My code automatically counts by 2 to account for my unmonitored right leg, and then I divide by the total elapsed time to get my cadence. My ground contact time was measured using a dual gate threshold on the accelerometer's total 3-dimensional force. So a digital stopwatch starts the millisecond a foot strike shoots past that 3.5 G, and then it will stop the instant that the force drops below 1.2 G, because this is usually right around where the foot pushes off into the air. And finally, my vertical oscillation was measured by subtracting my ground contact time from my total stride time to find my exact, I guess you could kind of say, flight time in the air, and then running that through a standard kinematic free fall equation. As the surface becomes softer and less predictable, my vertical oscillation drastically increased from just half a centimeter on asphalt to nearly 4 centimeters on sand, because my body instinctively had to jump higher in the air to escape the sand and the turf pellets. An important thing to note is that you can't compare vertical oscillations between the watch and Arduino, because the watch measures how much your center of mass moves as you run, so it will lower as you take a step and then go higher when you're in the air. My shin, on the other hand, doesn't drop below the pavement. Because my tracker is mounted to my shin, it completely bypasses the compression of the hips and knees, so it only calculates the actual distance my shoe physically leaves the ground. Thank you.